Right, hi guys. One second. Right, let's get everything the right size. Welcome to the stream, guys. Who have we got here? We've got Amok, Eldritch, Hayes, Stepz, Andy Magic Knight, Acmafin, Mr. G, Old School Coda, Prince Phase, Foroy. I think that's everybody. Sin Lao, welcome to the stream, guys. Mr. G, hi guys. Let's read a little bit of the chat. I was thinking the other day actually that the A-star algorithm would be a good one to show on stream, because I'm using it in the fighting game that I've parked for a bit. And while you can't do a kind of fully fledged A-star algorithm, you can do something. If the number of nodes are small, then you can do something. So, well, actually, it's kind of A-star. It's Dijkstra's algorithm, so it's a kind of non-grid based version of that. So, cool. Hope you guys are well. I've actually been asleep for the past 2 hours. This lockdown has really kind of thrown my body clock out of whack. One sec. Thank you for the follow, Kodan. Welcome to the stream. Okay, yeah. So tonight we're going to continue the Let's Code 6502 stream. Today we're going to do arithmetic. Because it's something you guys are going to need, obviously. Let's just call this start. Let's put it somewhere. There we go. Actually, I probably don't need anything. I'm just gonna show you how various things work. Actually, I will put a basic upstart in, because we do want to probably run this at some point. Well, that's massive. Is the music at the right level? It seems a bit quiet, so. Let's just put that in, and we've got an entry point to look at then. Yeah, let me know if the music is too quiet. It seems like it might be a bit low. Or if it's too loud indeed, I can't really tell, to be honest. I have got some notes to follow, because I realised there's quite a lot to cover here. I want to make sure we do it in the right order. Hey Hypnotoad, welcome to the stream. I like the name, by the way. Great Futurama reference there. It's perfect, music fine, quiet. So it's quiet for some, fine for others. I don't want to make it too loud. And let me put my requests up just in case anybody does request anything. Thank you for the follow, VreezyDE. Welcome to the stream. There we go, cool. Yeah, so I wanted to start, I've been wanting to do this stream for a while. I've wanted to kind of show you guys arithmetic and how to do it, because it can be a bit confusing at first. No, not on Flubits for these streams. There's not really anything to share on this. It's more just kind of showing you, but I will share at the end of the stream. See, and then occasionally music goes really loud. So why are we going to do a stream on arithmetic? Well, the main reason we need to do a stream on arithmetic is because the 6502 only has two things that it can do. It can add and it can subtract. You know, it's a bit like, yeah, that tune really did come in quite loud. I'll knock it down a little bit. There's no normalization on these on this deep sieve thing, so hopefully that's alright now. Hey Fistmass at 2K4, welcome to the stream, dude. So we can only add and we can only subtract. So the simplest things are the 8-bit add and subtract. So if you take a number, you can add another number to it. and this will give you 4. It gets more complicated when you want to go higher than 255, and this is why we have the carry bit. So if you imagine doing maths at school, you were told to add kind of like this. You would take the first 2 numbers, you would add them together, you would get 11. So you would write 1, and then you would carry 1 over to the next. And we have this concept of a carry in 6502 as well. And then when you add these numbers, this is 1 and this is a 0 here, you add the carry bit and you get 2. So this is how you learn to do it at school. And it's pretty much the same with 6502, except instead of going from 0 to 9, you go from 0 to FF. So imagine the same thing. Imagine the same thing, but with numbers from 0 to FF. So we've got 0, 0 and FF here, 0, 0 and 0, 1, 0, 1 here. If we add these 2 together, we get 1, 0, 0. So you'd write 0, 0 here, you'd carry the 1, and then when you add these 2 together, you get 0, 0, and you add the 1, 0, 1. So it's the same thing as you do at school, but instead of going from 0 to 9, you go from 0 to 255 or FF. So this is why we have the carry bit. Now, the way this works is if you... God, that music does sound really loud. Yeah. So if you want to add 2 numbers together, add a larger number together. So say we do the same thing here, and we add 1. This will set the carry bit. It's important that you start with the carry bit clear, because you don't always know what state the carry bit is in. So you need to clear your carry bit before you do these things. But what this will do now is it will return 0, the accumulator will be 0, 0, but now the carry will be set. So then what you would do, say we wanted to add, yeah, let's do it like this. So let's create some 0 page locations. Let's just do it at FC. So say we put let's create a number and put it into our LSB and MSB. So that goes at so now our location in memory here contains this. Actually, this little endian. Remember, little endian means that the smallest bytes go first, the biggest bytes go second. I need to model music loud compared to me. Okay, let's knock that down. Hopefully that's a little bit better. So say we want to add now let's add 0101. So we know that the result here should be 0200. So how do we add this? So first of all, we start from the least significant byte and work our way up to the most significant byte. So we take the least significant byte, we clear the carry bit first, because we don't want to, I'll explain what the carry bit does in a minute, exactly what's happening with it. And then we add the least significant byte, which is 0, and let's actually add 0201, so we can see different numbers. So our least significant byte is 01, and we store that number MSB. Record the track separate. Yeah, I'm trying to do that, but the problem is Shotcut doesn't split the track, so I have to use Adobe Premiere, and Adobe Premiere is an awful piece of software. So when you add these two numbers together, what's going to happen is you're going to take this least significant number, which is FF at this point. It's going to add 1 to it, which is going to create 0, 0. But carry is now going to be set. Let's make this all. And when you store that number, you get 0, 0 in that location. So we've actually created this bit now. So then to do the second part, take the most significant byte. So taking this piece here. We're going to add the most significant byte from here. And that's going to create 0, 3. And the reason it's going to create 0, 3 is because we add 2 to 0, which is 2. But the carry bit is 1, so we also add that as well. So when we add it, it clears the carry bit. So an add is called an add with carry. That's why it's ADC and not ADD. And what that means is you add the number that you're giving plus the contents of the carry bit as well. You flush the contents of the carry bit out and add it to your number as well. So there you go, that's how you would do the 16-bit. If you wanted to do more, you can easily add more. So let's say we wanted to, let's make this number a bit higher. And let's mix it up a little bit. Let's put C0, 10, C0, F0. So the number we're looking at now is that, and let's knock this down a little bit to make it not use the carry on this bit. So, and what we're going to add is we're going to add that to it. So the number we're looking for will be 3302 F1. So let's go through that, because this is so again, clear the carry bit, we take the least significant byte, chapter 2, and we add our least significant byte from here, which is 0, 1. So this becomes F1, the carry stays clear, so the number F1 gets stored. Then we take the next section, which is this, so we load in C0, because this is what we stored here. We add the next section, which is 4, 2. The carry bit is still clear. We add these two together, we get 0, 2, and the carry bit gets set. Because C0 plus 4, 2 is 1, 0, 2. And we store that number. And then we do the final bit. And that number is 1, 0. We add our next number, which is 2, 2. The carry bit is set, so it's actually 10 plus 2, 2 plus 1. So this becomes 3, 3. And the carry bit is cleared. There we go, and that means we've now got 3302 F1, which is exactly what we wanted. And you can carry this on for as many bits as you need. So, hey Goblin Prince, welcome to the stream. Doing well, thank you. Yeah, so the important thing is when you start an addition like this, you need to know that the carry bit is clear. Sometimes you know this automatically, sometimes you don't. One thing to note is that the carry bit will always be clear at the end here. So if you're doing multiple additions, you could do one clear at the beginning, and then you could do this and it would work fine, because you know that the carry bit is always clear at the end. And the trick is you just got to remember, start with the least significant byte, work your way up. So always start with the lowest byte and work your way up byte at a time through it. Actually, let's make a fresh file for each one. Let's duplicate this. Really? Can't duplicate? Fine, I'll do it this way then. So the way I like to think about the carry bit is if your addition or subtraction takes a number along the number line. So think of the number line. So we go from 0, 0 all the way to FF, and then it wraps around again to 0, 0, and then carries on to FF. So if your addition moves this way, then the carry will get set. And it's important to know that, because if you go the other way, this will clear your carry. I'll show you why that's important now when we do subtraction. Damn it, I thought I was going to keep it nice and neat, but it didn't. So let's go into subtraction. Wow, I didn't save any of it. Let's have a look at this, the same thing with subtraction. So bearing in mind that the carry bit gets set when you move to the right, basically along this number line, and it gets cleared when you move to the left. So let me just explain again there. If you wanted to add, say you've got a 16-bit number, or say you've got a 24-bit number like this, but all you actually want to add is 1 to it, then you would just change these values here. So you add 1 here, you add 0 here, you add 0 here. And you might say, well, why do we bother adding these two as well? Well, if we do carry, we need to make sure they carry along. So if this number started as like that, then obviously when you add these values, the carry is going to propagate all the way through. So yeah, you just add 0. So just treat the number that you want, treat the numbers as the same length, the same bit length. So if you want to add an 8-bit number to a 24-bit number, treat the 8-bit number like a 24-bit number, but just padded with zeros. Right, let me undo that to keep the values there. So subtraction works pretty much the same way, except in reverse. So let's do D0. No, I'm not going to try and work that out in my head, so I'm going to grab the calculator and just do it in here, just so I can write a value in. Seems right. There we go. So we're going to do the same, but we're going to do it with subtraction. So the first thing to note is that because the carry gets cleared when we cross the line going the other way, you need to start with a carry set. So subtract with carry is a little bit different. So let's just comment out a second. If we were to take a number and subtract 0, 1 from it, we want that result to be 1. And if we set the carry bit, that's exactly what we get. However, if we clear the carry bit, what we actually get is 0. And the reason that happens is because with subtract, it's kind of the inverse. You treat it like the inverse of what the carry flag is. So if the carry flag is set, then you just subtract the number you've got. If the carry flag is cleared, then you subtract the number you've got plus another 1. You can kind of think of it like when you do subtraction at school, it's called borrow. You borrow 1 from the next one. And borrow and carry are kind of opposite concepts. So you just have to remember that the carry flag is used to do both carry and borrow. It's called the carry flag, but you use it for borrow as well. Borrow just basically means if you've got 1, then your borrow is 0. If you've got 0, then your borrow is 1. So I'm going to write B in here so you know that, in fact I'll write borrow. Borrow is inverse of carry. So with that in mind, let's do a subtract. So we want to take our number, which is this one here, and we want to subtract this number here. So again, we start with the least significant bit, and we subtract our numbers as we go along. So thank you for the follow, Vita. Welcome to the stream, dude. Am I thinking about this right? Do we do most significant bit first? I don't remember. We'll see in a minute anyway. I can run this and test it just to show that it's working. I rarely do subtractions more than 8-bit, but you should know how to do them. And I'm actually doubting myself now with this. No, I think this is fine. Yeah. Why has everyone got a green name in chat? That's a good point, actually. Loads of people have. Yeah. I'm not sure why. Interesting. Oops. Let me give that page a refresh. Twitch is being really funny today. I'm not sure why. Okay, so subtract. Remember, we start with the carry set, basically. So we set the carry bit, we subtract 1 from it. We subtract 1 from our least significant value because we subtract 4 because our lowest value here is 4. That will give us EC, and the carry bit will still be set to 1, which means the borrow is still at 0. And then we store that value, and then we move on to the next byte, which is C0 here, and we want to subtract D0 from it. So the carry is still set at this point. So C0 minus D0 will give us F0, because we go backwards. You know, we need to subtract 1. So we've gone less than 0. Basically, we've gone 1 0 less than 0, which gives us F0. At this point, the carry will be cleared because we've moved this way. So we've gone from C0, which is here somewhere. We've moved D0 this way, which has taken us to F0, and cleared the carry bit. So now our borrow is 1. And because our carry is clear, and we store that number here, so which means when we do the last one, we take our number here, which is 1 0, and we subtract 0 1 from it, We take 10, we subtract 0, 1, we get 0f, but our borrow is 1. So because our borrow is 1, that's actually 0e is what we end up with, because 1, 0 minus 0, 1 is 0f, but the borrow is set, so we subtract another 1, which gives us 0e, and then we store that. Let's just stick a jump in the end here, and let's just run that and just demonstrate that working in the debugger. Okay. Apparently that doesn't want to run. Let's look up start 2, probably helps. Okay, so this has run, doesn't look like anything because we're not actually printing anything, but you can see the code has run through here. Just make this big enough so you guys can see it. If we have a look at our number in here, you see EC F0 OE, which is exactly what we wanted. EC F0 OE. Why does the live stream chat shown on screen capitalize? Oh yeah, it does, doesn't it? That's really interesting. It does. You're right. That must be a bug because that's using. I think that's using CapChat still, so I'm not sure why that's doing that. Because it's not doing it on my Edge screen here. Interesting. Okay. Pay attention. Who are you telling to pay attention? Thank you for the follow. Undefined behavior. Oh, Vita app as well. I missed that one. Thank you for the follow, guys. Welcome to the stream. And likewise with the subtraction, the carry bit here is always set. So it's the opposite of addition. With addition, the carry flag is always clear. With subtraction, the carry flag is always set. So you start with it set, you end with it set. So it's a kind of nice, it's a nice system because you know whatever you start with the carry flag set as, it will end up with set like that as well. So that's addition and subtraction, and you can carry that through as many bits as you want. Like I say, I rarely do subtraction of more than a single byte, but this is how you would do it, and you can stretch this out to, so this is 24-bit, you can stretch this out as far as you want. Right. What have I got next on the list? Oh, signed numbers. So signed numbers work pretty much the same way. You can do everything exactly the same as you do here. The difference to remember here is that when you reach a certain point in your most significant bit, your highest bit here, your highest byte here, you will cross a boundary. So with our number line, let's get rid of these F0 in here and this C0 here. There are boundaries here and here at 80 where you cross into negative numbers. So it's important to know that this will work exactly as it does for negative for unsigned integers as it does for signed integers. But when you hit this point in your most significant bit, you actually overflow and you become it's called overflow. I'll show you the overflow flag in a second because it's something we've never explained. So you basically go from having a really high positive number overflowing into a really low negative number. It's the same as if you didn't if you push the number all the way up to, so in a 24-bit number, if you had that and then you add 1 to it, what you're going to get is, and it's the same thing with negative numbers as well. So if you did this and you add 1, you'll get this, and it's just opposite ends of the scale. Basically, you're just overflowing the number line. So let's just explain the overflow flag very quickly. So the overflow flag is something that's not used all that often. In fact, I don't think I deliberately use it anywhere. Not that I can think of anyway. But basically, it's kind of quite misunderstood, and probably because nobody ever really needs it. So I'll explain very quickly what it does. It's quite simple. There's only 2 operations which directly affect it. There's actually 1, 2, 3, 4 operations that affect it. So the operations that directly affect it are add, subtract, and then you've also got pull processor status and RTI, which can both affect it as well. The reason for this is because these basically do, an RTI is basically doing a pull processor flag anyway, which is something I always knew, but I think I can't remember it was, I think it might have been Andy that reminded me that actually I don't need to store processor flag state for BCDs, but that's a whole other thing. We'll maybe get onto BCDs later, but these 2 don't directly affect it. They just restore the flag state. You can see the overflow flag in here. It's this one here, B. Actually, I'm telling a lie. There is a third one that affects it, but it's even less likely you'll use it for this. So it's this one here, which I can't click to for some reason. Yeah, I can't click on it for some reason. But yeah, it's this one under the V here. So the third operation that can affect it is a bit. So we've talked about bit before. Bit is like an AND, but it doesn't destroy the accumulator. And what this means is that if a value has bit 7 set, so if you bit the accumulator with a location that has FF, let's call it FF, but let's say that location has got FF in it. If flag 7 is set, you'll set the negative flag. It's exactly what you get when you set AND. Bit has the unusual thing, but it also sets the overflow flag if bit 6 is set. And if bit 7, V, if bit 6. I've never needed this ever. This behavior of bit, it's not something I've ever needed to do. So, but these are the 2 that are important. So what does the overflow flag do? Basically, the overflow flag is any time you cross this boundary, this sign boundary here, the overflow flag will get set. So I believe it works the other way for subtract as well. I can't remember if it clears it or not. Well, we'll do a little test here anyway now. So if you take the number 70 and you add 01 to it, we'll just put a jump in here so we can jump to this location. So I'm going to get rid of this, put it here. So we'll have a look what this does in the debugger now. So you can see our value in the accumulator is 71, which is exactly what we expect, and the overflow flag is clear. Now if we were to add 10 to this, you can see we've got 80, which is what we'd expect, but now the overflow flag is set, and that's because we've switched from a positive number to a negative number. We've overflowed from basically, we've gone from the number line goes from 00 all the way up to FF with 80 in the middle. But in signed numbers, this is 0 to 127, then minus 128, I think, something like that. Yeah. All the way up to -1. So in this case, we've crossed this break basically from a positive number to a negative number. We've overflowed. We can no longer represent a positive number beyond this point. Beyond this point, the numbers become negative numbers. So this is what the overflow flag does. I'll put a little note in here. Set when we cross the boundary from so positive to negative. Now I need to check this works in reverse as well, so I'm going to do, because I don't actually know, but as I say, I never really use this, so I'm going to do a quick check just to see what happens. I should probably use Easy6502, so I don't know what tunes have we got on? I've got Bob's Modern Favourites on. Let me put some different tunes on actually. I do want some games. Let's have a look. So it's favourite 100. There we go. Hopefully you guys can hear that. It's probably really quiet now. So let's have a look what's happened here. Yeah, so the overflow flag does get set if you go the other way as well. It's not just going positive to negative, it's also going negative to positive as well. So it's any time you cross that boundary, basically. You see here the negative flag is indeed set to 1. Our value is 70, correct. There are some cases where you can use the overflow flag to help you do certain things, but everything I've done so far doesn't actually require it. So somebody posted some code the other day. They were looking for a solution to something, and the trick was to use the overflow flag. I can't remember what it was for the life of me now. So okay, so that's addition and subtraction. So you'd think that, you know, multiplication and division is just a combination of using these two, but it's a little bit trickier than that. So if you wanted to multiply two quite high numbers, let's say you wanted to multiply, it doesn't even have to be that high, 10 by 10, right? The way you think about this mathematically is 10 times 10 is 10 plus 10 plus 10 10 times, right? But obviously that's going to eat your cycles. That's going to take quite a lot. So there's tricks you can do to do this. So the next thing we're going to look at is shifting. So we've talked about, let's put a new file in here. We've talked about shifting a little bit on various streams. Let's keep this bit the same. Why am I bringing it up in arithmetic? Well, shifting is cool because it's basically multiplying something by 2, dividing something by 2. If you think about a decimal number, if you've got the number 10 and you want to multiply by 10, you shift it all to the left by 1, which is basically adding a 0 on the end. And if you want to divide by 10, you shift it to the right, you knock a 0 off the end, and that's because we're in base 10. So shifting a number in a particular base is multiplying it by whatever base you're in. So in base 2, which is what our numbers are on the processor, if you've got 10, you do the same again. You add a 0, or you knock a 0 off, except now it's in binary, so it's times it by 2, or divided by 2. Thank you for the follow, CLCXE. Welcome to the stream, dude. Next week said 80 with half carry. Yeah, so I got another Game Boy actually today. Sorry, yesterday. I got it for 15 quid. I'm quite pleased with that. Just because it didn't have a battery thing on the back, so it's fine. I got a 3D printer there. I can print one quite easily. I thought for £15, why not? It gives me another system to try it on. I don't really need to, but why not? It came with a, is it Spyro or something? It came with another game. So shifting, yeah. So if we want to do division or multiplication by powers of 2, it's really simple to do. So if we've got a number such as 1, and we want to multiply by 2, it's as simple as basically, as I say, add in the zeros on the right hand side. So to do that, you shift everything to the left. So we use arithmetic shift left. And now accumulator is 2. So if you want to multiply by 4, you just do it again. And so on. So before we go into non-powers of 2, I'm going to show you how to do shifts across multiple bits as well, and also how to do it with sign numbers as well. I think it is actually going through all the music. This is track 4 from Last Ninja 1. Whatever that might be. Yeah, there doesn't seem to be any normalization of the music, which is a bit frustrating. I could probably put something into my desktop audio to do that. Actually, let me just have a quick look. We might be able to do that very easily. Where is my desktop audio? Does it not show on here? Or do I have to do it through here? Filters, there we go. It's got to be a normalizer on here. Normalize, no, compressor. I'll have a look at that at a later date. Don't know what I pressed there. Yeah, non-normalized audio is a pain. It really frustrates me. I used to hate it when TV would have that as well. I mean, they've got a lot better at it recently, but it used to be you'd watch a program, then the adverts would come on, and the adverts would be really loud because they didn't normalize any of the audio. I'm thinking, God, like, you know, the price they must pay for their mixing, their audio visual mixing desks, and they don't bother to hit a compressor or a normalizer on it anywhere. It's just, that's really bad kind of stuff. So you need to hear the ads from, yeah, that's a good point actually. So let's do the opposite. Let's do divide by 2. So we've already got 8 here, but let's go the other way. So if we've got 8 and we want to divide by 2, we use LSR, which is logical shift right. That will give us 04. So divide by 4 is just do it again. And so by 8, it's just do it again. And so on. It's worth noting that this will round any values you've got as well. Actually, I think it's not really a round, it's more of a floor. So if you imagine the number 9 here, actually let's do 13. No, 15 is probably the best one, best example. If you were to shift this, you would actually get 0. What do you get actually? You'd get you'd get 0, 7. So it's 15, but if you divide 2, that's 7.5, but that half bit doesn't exist. It's, you can imagine that being, and then when you shift that, your half bit's there. Actually, this is actually in the carry flag now. So your shift operations will move the bits that they move off the ends into the carry flag. So if you really wanted to take account of that half, you could, it's here, but you rarely need to think about floating point numbers or anything. When is an example when you would use a table? I'm going to show you some tricks with tables later on. I've got it in my list of things to look at. And I'll go through them in a minute. Probably after the break anyway. So yeah, let's do this one. So then you get 7, you divide that by 2, you get 3 because it's 3.5, and you divide 3 by 2, you get 1. So dividing 15 by 8 gives you 1, and that's because what this is doing is this is flooring every value as it comes through. So this is, if you take 15, you divide it by 8, you get 1 point whatever. I'd say it'd be 1.87 or something like that. Or 1.8675 or something. No, 1.875, whatever. The point is that it floors it and it takes that value off. So you're just left with the integer. So how do we do this over multiple bits as well? So let's set these values up like we did before. Let's just do it with 2. I'm not going to bother showing the 24-bit. We know how the 24-bit works. Basically, anytime we do a 16-bit, what I'm telling you will extend to 24-bit if you just repeat the last block of operations. Or as you'll see when we do sign shifting, you have to do them in a different order. In fact, shifting in general, you would do in a different order. So let's start with the one that we know. Multiply the easy one that we know, multiplying by 2. So say we want to multiply by 2. So with shifting, you need to shift from the right direction. And the way I remember it is if you're doing a left shift, then you start with the byte on the left. Think of everything in little endian. So we're going to do a left shift, which is this one here. Start with the byte on the left. So we start with the LSB. So we're going to load. And the reason you need to do that is if you look at a number in binary, so if you look at this number in binary, just put it here in binary. Okay, so this number written out in full 16-bit binary number is 1234. And so if we want to shift this to the left, basically we're putting a 0 here and we're moving everything this way. So you need to start with the lowest one so you can start moving. You basically push something on this side and shift everything along. So that's what we're looking to get. And this value is 2. This is 2, 1. E0 is what we're looking for in the end here. Is that right? Yeah. 21 E0. Yeah, that's right. Okay. Oops, that's too big. So how do we do that? Right, we take the first number, and the first number we always do with a straightforward shift all the time. So we just do a shift to the left, and we can now store that number here. Now what that's going to do is it's going to take our number. Let me display it in binary here. So our little endian number is thanks for the resub, Hayes. 7 months, awesome. Kim, indeed, yeah. I do love that. That's my favourite thing ever. That alert. Slightly embarrassing, but I've kind of got used to it now. So when we shift it to the left, what's going to happen is shifting it to left just moves all the bits this way and puts a 0 on this side. So if you imagine 1, 2, 3, 4, 1, 2, 3, 4, 5, we put a 0 on this end, which means this bit gets shifted out and let's put in the carry here. It doesn't matter what the carry is at this point because the carry does not affect this operation at all. However, this operation does shift whatever's in this position into the carry flag. So now our number in here, with the carry flag set at this point, is yeah, that's correct, which is E0. So that's our first shift. We've got that correct. We've got that here. That's what we want. Okay. And yeah, it always puts a 0 in. This operation always puts a 0 on the. So if you're shifting to the left, this will put a 0 on the right. If you shift to the right, it will put a 0 on the left. So then to do the next bit here, this 1, 0, this number MSB, we need to shift again. Now, if we just did this, this wouldn't work. I'll explain why that wouldn't work. Let's take a look at it, right? So, our carry is 1, and our number here is 1, 0, so it's... If we shift this to the left, like so, the carry flag is going to get cleared, because this gets moved into it, and then everything else gets put in there and a 0 gets added to the end. But that's incorrect because we want this 1 has crossed over, you see, it's been taken from here and we want it to go here. And so this is why we use a roll operation, it's called. And you use this you don't use it on the least significant byte, you just do a normal shift on the least significant byte, and then every other byte after that you use a roll. And what roll does is it takes the contents of the carry flag. So let's just go through this again. It takes the contents of the carry flag, and instead of putting a 0 on the right hand side, so remember I said if you shift to the left it puts a 0 on the right hand side. If you roll to the left it puts the contents of the carry on the right hand side. In this case carry is 1, so that goes there. And again the contents of the bit on that side going to the carry flag, so carry is 0 at this point. Which now means that we have this number oh my god, and that is equal to 21, and then we've got the number that we need. As say, if you want to continue this on, always use roll. Always use a roll on the subsequent bytes. You use a shift on the first one, use rolls on following ones. And that multiplies by 2. Now, if you want to multiply by 4, then you need to do this a step at a time. You can't just do that and that. That's not going to work. What you would need to do is you would need to do this, then you would need to do this again, and so on. So this would be multiplied by 4. Multiplied by 2 again. Now, generally what you will do when you do something like this, or the way I tend to do it anyway, is I will have, if I'm using 2 numbers like this, if I'm using a 16-bit, and I want to multiply by 4, what I will do is I will I'll take my least significant number, I'll do a shift, and I don't store it anywhere. And what I do is I directly roll so this is basically doing the same as load the accumulator with number MSB, roll, and then store the number in MSB. But what it doesn't do is actually use the accumulator, so then we can just repeat that. And then at the end, and if you wanted to do that with 24-bit, you can do the same thing. So you load the least significant bit into this one. And there you go. So this is a much neater way of doing this. This is quite inefficient, but I did it like this to show you how this would work. So this is multiplied by 4. And basically you would just repeat this, this little block. Each one of those blocks is a times by 2, so this is actually times by 8, and so on. Yeah, you can roll an address directly as well, so you don't actually need to have it in the accumulator to do it. You can roll a number directly, which makes these things much more efficient. So with that in mind, let's do a divide, but we'll use the optimization technique. So divide. Thanks for the host, Hayes. So we're going to do a divide by 4 optimized. So we're going to start by loading our number into the our least significant bit, and at the end we're going to store that back again. And we just do the opposite basically. So we shift to the right and then roll. However, this is the important thing. We need to do it the other way around now. So now, because when you do a shift, as I say, when you do a shift, you look at the number in little endian format. I want to shift to the left, so I'm going to start with the left value. If you want to shift to the right, you want to start with the right value. So in this case, we actually need to start with the MSB. Store the MSB at the end and roll the LSBs as we go along. Always remember that if you shift to the right, Rory's just amazing. If you shift to the right, you need to start from the rightmost byte. Thinking about it in little endian format. If you shift to the left, you need to shift the leftmost byte. Start with the leftmost byte. So to do this times in 16-bit, you do it like that. There we go. I'm just going to indent that so you can see we load the number here. Start with MSB for right shift. Shift to the right equals start with rightmost bit, so endian equals MSB. I'm going to leave this in here because this is a handy thing to remember. And so if we want to do this with 24-bit, we would take the highest value here and work our way down through the values. Like so, and that's divide. This is divide by 4 in 24-bit. What's the yellow stuff in the bottle? This is just orange. Got these things. Actually, this is the lemon and lime one. Nothing interesting. It's not pee. If it was, I wouldn't be drinking it. That's for sure. Okay, I'm going to take a quick break, guys. When I come back, I will show you how to do shifts with signed numbers, because signed numbers make things a little bit more complicated. Well, actually, they make things more complicated for right shift. They don't make things more complicated for left shift, and I will show you that. So we'll do that. Then when I come back, I'll show you how to use shifts to do multiply and divides that aren't powers of 2. Right, and I'm back. So let's make another one. Let's call it multiplication. Now, multiplication. So save it. Multiplication. Let's just copy our stuff from the beginning up here. Usually you only need to multiply by powers of 2. There are a few cases where you would need to multiply by anything else. Probably the most common thing you'll do on the Commodore anyway, I don't know how this applies to other systems, is to multiply by 40. And the reason for that is you've got screen made of 40 characters on a row, so sometimes you need to multiply by 40. When I multiply by 40, the simplest way to do this is with a lookup table. It's quick. You only need to multiply for 25 rows. And so I'd create a table. So I'd have an LSB table here, which would just be 25 rows, and then times 40, or 28 in hex, and take the LSB of that, the MSB like that, and so now I can take a number and multiply it by 40. So the way I would do that would be I'd take my number, say 5, and now I'll just load and store that in my And to be honest, for the most part, tables like this will be fine. Multiplying by 40 using a table. And you'll see this in almost every game. There will be some code like this. It's usually used for collision, things like that, just to kind of given an X and a Y value. What you tend to do is you get a sprite value, a sprite position. You will subtract the borders from that value, then you will divide by 8 to turn it into character space, and then you'll use the X and Y values that you get to look up. You'll look up the row in the table like this, and then use this value here with Y. So say I want the 5th row and the 8th character. I can use the 0-page indexed addressing mode, indirect indexed addressing mode, to grab the value at that position. What you would do is you would add your screen RAM address on here. So if you now when I look these up, this is going to point directly to a value on screen. We can test this out. So if we put a 0 in here, store it here. Actually, let's do this. So this is actually the Y, even though it's in the X. So this is actually at 8,5 on screen, because we're looking up the row first, which is our Y, which is this bit here, and then the X column here. So if I just do a quick test of that, we should see, you can see there, we've drawn a little and symbol here. So this is the common way of doing multiplication using tables, and this is probably what you'll see the most on the C64. But it's not always the best way to do it. So sometimes you might want to do something like multiply by 3. So if you want to multiply by 3, if you've got a number, say this, and you want to multiply that by 3, now you can either add it to itself 3 times, create a label, call it temp here, or what you can do is you can store it in temp, then you can shift it to the left, which is times by 2, and then you can add temp, and now you've got times 3. So you kind of have to think about multiplication in this way, and usually you'll find that a table is probably better. Again, in this case, a table would probably be better. So if you had a table called times 3, you could fill this with let's do up to 85, which gives us 255. So now we can do any multiplication of a number up to 85 times 3, and that would be you take your number that you want to multiply, say 10, and then you load times 3, comma x, and you can see that's much quicker than doing this. However, this is only going to work in 8 bits. You'd have to create additional tables. So if you wanted to go higher, you'd have to create another table here. And do it like this. So really multiplying and dividing by numbers that are non-powers of 2 comes down to, do I need to do it as a table, or do I need to use a method like this? Generally you'll find tables are going to be the easiest way to do things, and certainly going to be the fastest way to do things. But there are other ways to do it as well. There are actually on Codebase routines that will do this for you as well. Trying to think of where's my browser. Let me just get the browser. I'm not going to go through these routines, but I will post a link to these maths and algorithms. Yeah, so there's routines like this. I'm going to post it in here. This is in I'm not sure what format this is in, but there are routines like this which will loop through values and give you multiplications as well. I prefer to, if I have to do a multiplication and it has to be in a non-power of 2, I will try and use a table. So there's a code link to that, and the page with all this maths on is here as well. What I am going to show you though is a really sneaky way to do division, because division is something division is something that you will probably want to use more than multiplication for various things. Timers and stuff sometimes need to be divided by 3 for various things, and I can show you a sneaky way of doing divisions as well. So let's do another file. I'll show you how to do divisions. So one thing I found when I've been doing code is sort of spamming links. This is a wholesome stream. One thing I found when doing division is that I haven't done sign shifts. I'll go back to them in a minute, because it's important to know how to do a sign shift with right shift. So you've done divisions that returns binary fractions too, yeah. One thing I found when doing division is most of the time when I want to do a division, I only need an approximate result. So, for instance, if I was to divide a number by 3, now if I've got, say, the number 100 and I want to divide that by 3, essentially what you're doing is you're saying, how many times do I need to add 3 together to give me this? So obviously the answer here is 33.333, right? Now that's going to be slow, because that means you're going to have to keep subtracting 3 from here until you've done it 33 times, and that's going to take quite a long time to do. The way I like to think about it is, how do I turn this into a combination of shifts, or as close to a combination of shifts as possible? So 100 divided by 3 is also the same as 100 times 0.3333. Because this is 1 over 3. So we're inverting this into a multiplication instead. And you can think of times 0.3333 as times as a composite of multiple multiplications. So if you want to get 0.323, think of the powers at the 1 over the power of 2. So 1 over 4 is 0.25, and then that leaves us with 0.08. So 1 over 8 is no good, because that's 0.125. 1 over 16 gives us 0.067. No, 0.625, which gives us 0.3125. So that's getting fairly close. So let's try adding another one onto here as well. So the next one will be 0.03125, which gives us 0.345. I'd say for what we want to do, if you want to approximate value, this is probably close enough. In fact, I would probably go with this one. I think this is close enough. So how do we do that? Okay, so if we take a number, say, let's take 128 and we'll divide it by 3. Oh no, let's do 100 by 3. So 100 is 64 in hexadecimal. Well, that sounds loud. This is why the edges in Tomb Raider never met properly. Yeah, it probably is. So what do we want to do? We want to divide this by 1 over 4. 1 over 4 is 1 over 16. So we want to divide it by 4 and then divide it by 16 and add the results together. So the easiest way to do this is you take your number, shift it to the right twice. At this point we have divided by 4. And we store that in a temporary label somewhere. Let's just put it in here, it's fine. And then we shift it again by 2, so it's now divided by 16. We need to do it here, and then we clear our carry bit and add the temp value. Which is now multiplied by 0.3125. Again, this will only ever be an approximation, and depending on how accurate you do this calculation up here is how accurate your thing is. So let's have a look at what we get at the other end of that. So the number we're aiming for is 33.3. I think we're going to get probably 32 or 34 out of this. if you skip the CLC, you get slightly more accurate. Is that true? Oh yeah, it would be, wouldn't it? Because you would get. Let me think about that. Oh yeah, you're right. Because if the value, if this last bit of the value here, it's going to add 1 to it. So let's try it with and without. So let's do it without first. So let's have a look. So we've got to this point. The accumulator is actually at 31 at this point. So we're out by 2 here. So let's do it without the clear carry bit. Yeah, it's a good tip. I never thought of that. It's really, really good point. It hasn't worked for this because the last bit was clear at that point. So it's still the same value, but you can see how you can kind of work this out. So if you wanted to do divide by 5, for instance, divide by 5 is so let's put a point in here. As I say, usually these approximations are good enough for what you need to do. So for instance, I had something where I had an amount of time to display three items, and I needed to make sure that the amount of time that they were displayed for was shared equally between them. So we're talking about a frame here and there. And so that meant that if you removed one of the items, yeah, I'd need to divide by 2. If I had 3, I needed to divide by 3. If I had 1, I needed 1, and so on. I think it's in .cosmos 2. It's in the timing routine for the freeze. So you've got a little power bar at the bottom, and the amount of time it takes for that power bar to dissipate depends. Sorry, the amount of time that your freeze stays on screen depends on this value in the bottom, which meant I had to work out what the time was for each thing. So divide by 3. Okay. So actually, in this case, you probably want to set the carry bit here, because this will round this value up. So yeah, in this case, you would want to set the carry bit. So let's put a little note in here. I'm going to copy exactly what Aquafin and Carl are saying there. Which way your tolerance is. So in our case, we're under. This value is under, so we'd set the carry bit so it goes higher. So now if we show this, I think I've got like 12 bloody things open. You see it's set to 20, so we've actually, yeah, we have got more accuracy. This actually goes to 32, so it's not bad. It's not bad at all. So let's do divide by 5. So divide by 5 should give us 20. So let's see how close we can get to that. So it's the same as 1 over 5 is times 0.2. 0.2 is 125, which is 1/8. Plus this would give us 1875. That's not close enough for my liking, so let's add another one on here. 0.03125. It's going to be 2. Let's do another one. So this would be 0.15625. So this is 1 over 8 plus 1 over 16 plus 1 over 64, which gives us 9 2 0 2 5 blah 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 blah. This is kind of close enough. So how do we do that? So take our number and we divide by 8. So we half it again. Now at this point we need to add 3 numbers, so we're going to push the current number that we've got. We're going to add it to temp, store it back in temp, pull the accumulator from the stack, and then we're going to shift it again twice, and then add temp back again. So it's a little bit more complicated this time. You need to think about each one individually. Ah, yeah, that's a good point. Yeah. Oh, yeah, so actually there's a really simple way to do this. So, yeah, actually, that's a really good point, Carl. Let's do this one, and then I'm going to show what Carl's saying there, because actually we can get this spot on accurate. This is quite cycle heavy, so... Oops, let's do it in the debugger. Let's close all the debugger windows. You see, we have got an accurate number, so our number is at 14 here, which is 20. So this has actually done a proper divide by 5. But you can see cycle-wise that's quite heavy. So let's do the same thing again using this technique. Can we get it more accurate? I think we can. No, we can't actually, can we? It's going to be... We could have 0.25 minus 0.0625. Yeah, so it's not going to be more accurate in this case, but yeah, I see what you're saying there. It's all about using powers of 2 to generate these kind of decimal values, these floating point values that are as close as you can, just by using combinations of 1 over a power of 2. Okay, before we move on to onto the next step, I just want to go back to shift in a second. I want to show you some other stuff. So shift and assign number to the left is quite simple, because hang on, is it quite simple? Think about it. I know shifting to the right is definitely... Okay, shifting to the left. You start with the left amount, right? Let's say we've got... Yeah, it's fine, you just get overflows, that's all. Okay, so this is a negative number, right? And this is actually minus 1, 2, minus 16, I think, yeah. I really get confused thinking about the minus numbers. And so to shift this to the left is going to give us... oops, not on this line. Let's put it in. So shifting this to the left means we're going to put a 0 on this end and knock 1 off the end here, which is now E0. Which is minus 32. And see that's the same as multiplying by 2 up here. It doesn't really change. And if you want to do this with 16-bit numbers, it's exactly the same. So if we take our faster way of doing it here, let's put a huge negative number in here. So let's put 40. Let's put C0 here. So this is C040, which equals, and I can never work this out, so I do have a page that, if you want to convert numbers, by the way, if you go to this page here, you can put hexadecimal numbers in and work out what they are in terms of negative numbers. So that's -1, 6, 3, 20, and so this will divide this number by 2. And let's just put a jump in here. Let's give this a quick run and just have a look what comes out the other end. So we're looking for -32640. So we should have 7F80 at the end of here. That's what we're looking for. And if we go and have a look in our memory, where's it stored that? Oh, because it's overflowed, that's why. Let me change that number to one that's not going to overflow. Let's do it as F0. .032, right, so we're looking for double this, which is 8064 minus 8064 should give us E080 here. But you see what happened there is the number overflow. Interestingly, the rolls like this will not set the overflow flag, so you can't rely on that to know when you've overrun. And if I have a look in here, oh, it's not. Why is this not working? C100. What am I doing wrong here? Starting with the least significant bit, yes. Shifting it, rolling. Oh, because I'm doing times by 4. That's why. There we go. Might work a bit better now. Yeah, there you go. E080, exactly what we want. So shifting to the left with sign numbers is pretty much the same as you would expect with non-sign numbers. Now it gets a bit trickier when you want to shift things to the right. So if we take a negative number like this, we'll do the same thing again. Now, if we were to just do what we do for, where's our divide? Oh, I've actually not put the divide in here. Okay, so divide we start, because we're shifting to the right now, we start with the rightmost bit, which is the MSB. And like I said, normally what you would do is you would do a normal shift. What's going on here? Yeah. Separate those up here. Do a normal shift. And then you would roll the next one down. And store. Now the problem is this isn't going to work, right? So we're trying to divide by 2. So the result we should get here should be minus 2016, which is F820. But let's see what happens when we do this. And what we actually get is 7820. We get that instead, which is wrong. And the reason this is wrong is because we're shifting bits to the right, which means that sign bit gets moved. So immediately the first thing that this does is it actually destroys the sign number. It becomes a positive number. So the way to get around this is really, really simple. All you do is you need to set the carry flag if that last bit is set. If it's negative, we need to set the carry flag. So the easiest way to do this is you take your MSB, your first number, and you compare with 80. And if this number is 80 or more, then it's going to set your carry flag, which means instead of doing a shift right here, you'll do a roll here instead. And now when we do this, we should get F820. Which helps if the thing's actually refreshing properly. Let's try and restart again. Why is it not restarting? Okay, try again. This is the only thing with a debugger, sometimes it can be a pain. Swap my headphones. Thank you for the follow, by the way. I've missed a couple here actually. Isabel, Chris267 and Puppy Codes. Thank you for the follows, guys. Okay, I don't know why this isn't being set in properly. This was all working and now it's just decided not to, so that's good. There we go, right, there we go. And if we're going to have a look down here, you see F820, we've got our number that we want. And this is the key thing, so when shifting sign numbers to right, MSB needs a compare 80 raw. Oops. And so if you wanna do this to divide by 4, you would just repeat the same thing again. So let's do this, divide by 4, and this should give us FC10 is what we're looking at the end here. And again, we just repeat this block in the same way that we were repeating this block here. Here. We just repeat this block here, and it's only the MSB that needs this. It's only the very most significant bit, and that's because the most significant bit is the one that has the sign. So I'm just going to replay one of my alerts because I think my alert noises have gone off. Oh no, they're still there. I'm just not hearing them. Yeah, thanks for the follows, guys. And you can see FC10. So it's an important thing to remember when you're doing signed numbers. Again, a lot of the time you probably won't need to work with signed numbers, but if you do, it's important to remember this little trick for shifting them. Okay, let's go back to division. I think this pretty much covers division. Again, like multiplication, if you're doing divides and you need very accurate values, use a table. It's going to be the fastest way, unless you've got like some crazy kind of 3D maths that you're doing where you need floating point divisions and stuff. This is going to be the easiest way to do it. Just use a table. So if you like, for instance, you need a very quick kind of divide by 5 or even a divide by 40 for whatever strange reason, you might need to go the other way. Then use a table, it's going to be quicker. It always comes down to, do you want to use more memory, or do you want more memory and faster code, or less memory and slower code? It's just it's a fight between the two. So strategy game wise, waiting requires full multiple. Yeah, I can imagine actually. So there are other tricks with divide as well. So if for instance, if you divide by 3, okay, say I've got a number such as 64, and I want to divide by 3, then no, is it divide or is it multiply? Hang on, let me think about this. I might be thinking of multiply. I was thinking about this last night. There's a way of doing bit shifting and using the state of the carry flag to work out whether or not you should be using a shift on your original value or not. I can't think of it offhand. If I remember before the end of the stream, I'll show it again. Yeah, to be honest, I haven't done much in the way of 3D stuff on the C64, so I think the most complicated kind of maths I've really had to do was probably some division stuff in Doc 2. That game has got so much stuff that I've done for the first time in it. It's kind of crazy. Okay, let's have another look at some other stuff to do with addition and subtraction. This time I'm gonna create a new file. I'm gonna call it scores. So one of the common reasons you might need to do addition and subtraction is for scoring. Usually just addition. Let's take this one. And the reason I want to cover this is because this series is about 6502. Now, most implementations of 6502 have what's called binary coded decimal mode. Actually, I'm going to rename this to BCD. There we go. So what is binary coded decimal mode? So binary coded decimal mode is a way of representing base 10 numbers using binary, and the way it does it is it splits a binary number into 2 nibbles like you would normally expect. BCD treats each nibble as a number, as a digit 0 to 9. So if we have this number, for instance, if we look at that in hexadecimal, this is where it gets interesting. So if we look at that in hexadecimal, it's 93. And this is what BCD is doing. BCD mode treats this number as 93, not as hexadecimal 93, but as 93. So if we were to take the number 93 and turn decimal mode on and use clear and set decimal, actually let's do a slightly lower number. Let's do 53. So and then I'm going to add 07 to it. Now, what you would, without this, what you'd expect is 5A. But with decimal mode on, what you'll actually get is 60, because 53 plus 7 is 60, so you will get 60. And we can see that if we just put that in the debugger. Value can't be resolved because I keep doing that. I need to put that back in here, and I keep copying that across. That's the wrong one. I'll put it in this one. There you can see there, just about in the top of this window, our value is 60, not 5A. If I turn this off, turn BCD mode off, we get 5A. Thank you for the follow, Mark Fletcher. Welcome to the stream, dude. So you can see it's a really useful way of doing scores, because if we wanted to have a score value, say we've got 6-digit score here. Let's call these let's say we've got a score of this, so we can store this in the same way as we do before. We do little endian as well. Doesn't need to be anything special, but we can store this score exactly like this. That's 7 digits. Yeah, you're right. Thank you, Accumulator. Let's put this at the top. So we'd store our score like that, and then say we want to add. Let's add 1000 to score. Let me just put this in here. Always remember to, when you've finished, always remember to disable it, because this affects every addition and subtraction that you do. It's the only thing it does affect, but it does affect them. So if you don't clear the decimal flag here, you'll cause all sorts of weird problems. So say you want to add 1000 to the score, so it's quite easy. You treat this again like a 24. So this is a 24-bit number, even though it's a decimal number. It's still 24-bit in memory. So we just treat it like a normal 24-bit number. So we'll treat it in 3 sections like this, and we start from the least significant bit. So we take score 0, 0. I will start with the carry bit clear because we're not sure what the carry bit is at this point. And we add the lowest part. And then we take the next byte along, and we add the next section. And then we do the same with the last bit as well. And in this case it's 0, 0. And remember to set the decimal flag here and clear the decimal flag here. And then when we go and look, our score should be, what would that be? It would be 020900, which is what we're looking at. And the carry flag works exactly the same here. So. The only difference is that when it does the addition and subtraction, it treats it. What have I done wrong here? Have I set the wrong value for the first one? Or have I set these in the wrong order? FCDE. FC. Oh, 020900. 020900. Perfect. Now, why is BCD useful? Why would you not just do this with, you know, normal kind of non-BCD values? The reason you would do this is for display purposes. For display purposes, this makes it really, really simple. So if I wanted to store this now on the display, I can basically take each value like this, and I can say, okay, I want the first nibble. So I can if I shift this to the right 4 times, I've now got a value for the first digit, which means if I clear that and add 30 to it and store that at 0400, I've got the first digit. I mean, I'm doing this the long way around, but you would do this in a much easier way. You could write a loop to do this, for instance, in a much neater way than this. And that's basically it. And it just makes converting things to on-screen scores much easier to do than trying to do this with let's just copy that on there, and trying to do this with non-BCD values. So it's quite long, but you would write a loop for this. So let's see, do we get 020900 on the screen when I run this? I can just do this with F7 kind of. And there you go, 020900. So you can see how easily that is to work. Yeah. Let's read a bit more of this. As long as it works, yeah. Hey C64Psy, welcome to the stream, dude. Now, why do I bring up BCD? Well, partly because I want you guys who are using systems that have BCD, which is most 6502 systems, to be able to do scores in an easy way, and this is a really simple way to draw scores. However, if you look at a system like the NES, it doesn't have a BCD mode, so that means you can't use this method. So instead, what I like to do is, and I tend not to use BCD, I tend to use this second method instead anyway. What I tend to do is I use wherever the score display is, like so, as my kind of target. So I've drawn the score in that top corner here. This is now my score store. This is where my score is. And then what I will do is I will say, I want to add, I'm going to add another 1000 to it. So I'm going to add 1 with 3 zeros on the end. So digit value, and then trailing zeros. This is where it gets a little bit more common. I'm going to try and do this from memory. I have done this a few times. I think we're using this actually in the game, the Saturday game. I think we're using this method for it anyway. So what you do is you start by taking the rightmost value. We're going to store this in I'll call it vector 1. I'll call it score vector. Score vector, there we go. And I'll put that FA. So you store that at score vector plus 0, and you store. So we create an indirect lookup for score display. Oh, I've got a really itchy nose. In fact, I'm going to go for a quick break, guys. When I come back, we'll finish this, and then I'll take any questions that anybody's got, and I'll try and explain some other stuff as well. Alright, I'll be back in 2 minutes, guys. Be right back. Right, and I'm back. Da, 6502 virus, that would be good. Yeah, NES doesn't have BCD. That's why I tend not to use BCD, mainly because I was always afraid that my interrupts would screw up if I was setting BCD somewhere. But as Andy pointed out, and I should have known this really, that the interrupts, when you start an interrupt, your processor state is pushed to the stack and then it's restored anyway. So, and BCD mode doesn't get screwed up. So it's the 6502 that's slightly different. Yeah, it doesn't have BCD mode. So once you've got your score vector set up, you'd probably have this already set somewhere. You wouldn't do this every time, but I'm just going to do it here for the purposes of this. Then you need to set the Y register. This will be our digit that we want to start. So we start at the first digit, the units basically, which is index 5. And then the first thing we need to do is we need to ignore trailing zeros. So the way you do this is you compare x to 0. If it's equal to 0, we skip on. Otherwise, we'll decrease x, decrease y, and then jump to, I'll call it dex zeros like that, which is just this bit here. So basically, we're subtracting this value from this value. You could do this with a lookup table as well. I mean, you could. Yeah, I mean, this is going back to our subtraction thing. How do you want to do this? So if you wanted to do, you could also, for instance, instead of doing this, you could. Actually, we need to do this first, don't we? So that's our score set. You know, you could rearrange this a little bit, so you could say actually put our leading zeros, we'll store our leading zeros somewhere in a temp value. But it really doesn't matter. The end result is that you need to get this Y register to be 5 minus whatever this value is here. This will do it, and to be honest, it's not going to happen. You know, this isn't going to take too many cycles to do, so it's fine. Then what you need to do is you will load a value in our score vector, comma y, We will store the digit value that we want to add. We'll put that in temp, which I believe we've got set up. No, we haven't, so let's just create a temp up here. The reason we need to store it is because we're going to use the accumulator in various places here, so we're going to store it and then we add that value like so. Just check that's nothing important. It's not, that's fine. Cool. I just realised, did I actually press enter on? Oh, I did, okay. Sometimes I forget to press enter on my stream announcements, but I actually remember today, which is good. So now we've added this value to our temporary, and now what we need to do is we need to compare. So our characters go from 30 to 39. So if the value is 3A or more, we need to do something. So if it's less, we can go straight to the end, and we've done things correctly, and we've correctly incremented the value. In this case, our value at the end, this will work because this isn't actually incrementing it beyond that point. So we'll come to that in a minute. If it is more than this, then what you need to do is you then need to, the carry is set here, so you don't need to set it. You need to subtract 10 from it. We need to do a store at the end here. The last thing you need to do is store that value. And we would need to store that here. And now what we need to do is we need to put a 1 into temp, decrease the y, and jump to the loop here. And this will keep doing this. It will keep adding a value to each digit as it goes along until it doesn't carry over anymore. This is our carry, basically. It's our carry simulation, if you like. And so if we run this now, we should see we add 1000 to our display value. Our display value was 020900. So this should give us 021900 if I've done this right. This is asking a lot. What if I skipped here? Put that there we go. 021900. So you can see I've easily added 1000 to it here. So you can do additions like this in a number of ways. You could, if you wanted to add, say, 2500. You could add this value. In fact, let's make this a little routine. Let's put an RTS here. Let's put the jump at the end here. Let's call this add score. So if you wanted to add 2500, the way you would do this is you would add 2000 and then 500. And so 2500 would be 2, 3, 400 is what we expect here, if this has worked. And there you go, 2, 3, 400. So you can see you can still kind of work kind of in BCD without actually having BCD. We're treating the screen RAM as individual bytes. It's not really BCD because we're treating each byte as a number from 0 to 9. And all you need to do is adjust these values based on where your numbers are in the font. This is the default font. numbers in font go from 30 to 39. And you see it's quite easy. I mean, you can expand this a little bit as well. I think what we did in the game was actually we allowed you to do things like we actually allowed you to do something like for 25 you could have done it like this, like that instead. But this, I don't think this will work. Let's just try that. I don't think this will work. I think this is going to do something very strange. So 23400 is what we're looking for. Yeah, see, it's getting confused here. And the reason it's getting confused here is because now we're adding way more here to it. So there is other ways of doing it as well. If you want to see how to do that, the game code in GitHub, let me put a link to GitHub. The game code in GitHub does have this. I will show you very quickly. I believe in the, oh god, it's very messy, this thing as well. So I have no idea where it actually is, so we'll just have to look through until we find it. It's not going to be in there, is it? It's going to be, I actually don't know where it's going to be. Yeah, player HUD for some reason. So in here, yeah, we've got an add score here. So this is doing the same sort of thing. It's looking up a value on screen. It's actually looking at two different players here as well. And it's actually using the carry flag to do these things. But it's essentially the same sort of routine. You can see I'm using a temporary value to do the subtraction at the beginning. This bit that I was doing here, I've done it a different way in the game, using a temporary value and then subtracting x, which is our leading zeros, and we're using the carry bit to do things. So we're actually shifting out digits on each one as well. And we actually pass it in BCD format without actually using BCD. So we use shifting here to grab either the upper nibble or the lower nibble, depending on which one we need. So even though we never actually turn BCD mode on here, we're actually treating the values as BCD and passing them in. Okay, cool. That kind of explains BCD a little bit, I guess. So let's say add 2000, add 500. So this is how you would do it on the NES, basically. Let's put a whole breakpoint in here. Cool. I think that's pretty much it for what I wanted to cover. I have got some notes here. Table tricks, overflow. Yeah, okay. If anybody's got anything else they want me to look at or to explain, I can kind of go through that. I'm going to show you some, in the meantime, some table tricks. So let's call this one tables. So yeah, if anybody's got any questions or anything they want me to look at or to try and explain how I would go about doing something, please feel free to ask. I'm going to show you some stuff I do with tables now. So I generally have a table called plus, and this table probably won't make much sense at first. Try and keep an eye on stuff as well. So this table is basically just the values from 0 to 255. So why do I have this table? Okay, so the reason I have this table is because if I've got a number, say I've got the number 7, and I want to, in the X register, and I want to add 15 to it, I would normally have to do that, right? And this is ignoring this value here, right? This is 2 cycles, this is 2 cycles, this is 2 cycles, and this is 2 cycles. Or what I can do is I can just do and that does the same thing, but only takes 6 cycles. So this takes 4. Oops. This takes 2. So that takes 6 cycles. So this is a lot quicker. The only caveat with this is this isn't going to do overflows. If this gets to the end, it's going to start drawing whatever's on the other side. So one thing you can do, if you really don't care about memory, is you can fill 2 tables with the numbers, then you can add 255 and it will overflow. You're not going to get any carry flag on here, but if you just want to do small additions, it's a really simple way of doing it, and it saves you kind of, first of all, it means you don't have to mess with the carry flag. So if the carry flag is important, you can leave that as it is. Likewise, if you wanted to do this, for instance, you wanted to put it in the Y register, you're now using the X, the accumulator, and the Y register, whereas here you could just do this. It would take less cycles, take 4 cycles, and puts the value straight into Y register as well. So there's advantages to using this table. I tend to use this in my code. If I can afford to use a page of memory, then I will. Hey Warlock, welcome to the stream, dude. Okay, has anybody got anything they want me to explain in a bit more detail, or something I've not covered that they'd like me to? Let me write some stuff in here. I think I need to have a beard trim. This is starting to itch a little bit. If bushes. Oh, Accumulator. I'll tell you what I am going to do quickly. Trying to think what else I can show you guys with the arithmetic. Obviously tables are useful for signs as well. So obviously you wouldn't want to try and calculate sine and cosine. I mean, it can be done, but you would have to use floating point maths and all sorts. So the easiest way to do this is with a sinus table. And so what you'll commonly see is something like this. And this will give you values from, this is what I normally do, this will give you values from -127 to 127 on a sine wave. and then you would just basically, you would treat your angles, instead of 360 degrees, use bit table trick, bit command. Oh yeah, bit as well. So this is another reason to use the plus table. I'll show you that in a second. I'll insert that up here as well. Yeah, another great use of the bit table, of the plus table. So if you wanted to get the sign of 180 degrees, you pick a number in the middle, so 360 degrees in a circle, half is 180, so we have half of 256 because our angles that. So yeah, using plus table for bits. So bit is like and. So if you take a value like 0.7 and you AND it with 0.3, the end result will be that the accumulator is set to 3, the 0 is clear. In fact, if we do this with 87 and 83, we'll get the accumulator 3, 0 is clear, negative set. The problem here, obviously, is that if we want to then do another operation on this value, we then have to load it in again. Maybe we want to do something like that, right? So we have to do this again. We have to load this value in again. So what the bit operation does, hang on, let me just put a little note here. What the bit operation does is the same as an AND, with one exception. It sets the overflow flags I explained before. Well, I mean, all right, let me get rid of complex, because that isn't complex trig math, is it? I see what you're saying. What the bit operation lets you do is an AND, which sets these flags but doesn't trash the accumulator. However, it doesn't work in immediate mode, so you can't do this. It only works with addresses. So this is where the plus table comes in handy. So what you can do is you can do plus 83. And so now it's going to get the value 83 from this table and do a bit. So it doesn't work in immediate mode. So plus table helps. And now we get accumulator is still 87, and we still get the same results from above. So we get 0 is clear, negative set, which means we can then go ahead and test against another number and another number and another number. You know, we can keep doing it. So yeah, this plus table is really useful for that sort of stuff. I'm going to put that, actually I'm just going to leave it at the end. Yeah, I had to look at that a few times. Yeah, okay. How about finding the square root? Well, there are techniques for doing square root, so I couldn't tell you offhand, but there are definitely ways to do it. I've seen it on Codebase as well somewhere. Fast square root, there we go. yeah, I mean, it says it's fast, but it doesn't look that fast. But again, what I would do with square root is probably use a table for that as well. So if you want a square root of a number, you know, you just fill like so, and you'll get the square root quickly. There are ways to do this accurately with 16-bit numbers, and there is a great article on here. Again, it's another Codebase article. Codebase is really good if you want to kind of learn how to do these things. Codebase is a great place to go and grab all this stuff. You may have to convert them to Kick. They're not always in Kick format, but so I want the square root of 64, let's say, and then I can just load. So the square root of 64 is 8. So that's how I do square root anyway. I probably wouldn't go about doing this. Oh, one other thing to bear in mind as well with square roots is, so a common use for square root is distance calculations. So you might have two objects and you want to know if they're within a certain range. So e.g. is distance between two objects less than 10. So you may want to know if something is close enough. So normally you would do Pythagoras. So you would take square root of x2 minus x1 times x2 minus x1 plus y2 minus y1 times y2 minus y1. But the thing is what you're trying to find out here is not is the distance between them, right? So you can change this to get rid of the square root. So it becomes simpler. So you just need to check these two things. So you get these two values, you multiply them, multiply these two, and check if it's less than 100, and you remove the square root, so it becomes much simpler. All is well from what I can see from Sean's math. So yeah, this is a common kind of optimization that you will see, because generally you're using it for distance, and while this will give you the exact distance between the two objects, you actually don't care about the exact distance. You just care that it's less than a particular value, and as long as you don't mind squaring, multiplying this value first, doing a few multiplications, doing 3 multiplications is much quicker than doing 2 multiplications and then a square root of the result as well. And this is something you can use lookup tables for as well. So you would use a lookup table for these values here. So once you've got one value here, you would just look it up in a square table. So you could have and you would probably do this with MSB and LSB. So then you would take your value. So let's say we've pre-calculated this. and this value is now 20, for instance, and y2 minus y1 is 10. You would always kind of work out which one's higher than the other one and do it that way around. But let's say we pre-calculate these, you could then, let's just assume we're doing it with, and it wouldn't be with LSBs, would it? It would be, well, these are definitely going to be more. So we would take, so first of all, we take the square of this one, store it at, let's call it oops. So we've got this value now. I'm just going to create some values here. Results. Probably use 0 page for this as well, but so there we go. We've got the square of this value. Just move that up to here, and we can do the same with these values, and we need to add them to these values here. So clear and then and now result LSB and result MSB is our 16-bit value. And then you can do some comparisons there. So we want to check if it's less than 100. So the first thing we would do is low result of MSB. So if that value is positive, that means it's over 255. Sorry, if that number is more than 0, then it's over 255, so we've immediately failed, and then we can just check our LSB. And compare that to 100. We actually want 100, less than 100, so that's fine. So if it's 100 or more, go to fail. Otherwise, success. And we do something like, increase the border or whatever. So yeah, that's a really quick way of doing distance calculations without using square roots. And you can see we're not actually done any multiplication here; it's all done with tables. So by using 512 bytes plus 2 for our result, so 514 bytes, we've now got distance calculations that will allow us to do distances up to 255 on the X and Y, which is plenty for most cases. Hey Goku Vibe, any tips for someone who wants to get into coding? Oh, thank you for the follow, Avalanche Pointer. I'm going to call you Avalanche Pointer because PTR means pointer to me. Welcome to the stream, dude. Any tips for someone who wants to get into coding? Where should they start? Depends what you want to code. If you want to code retro stuff, my streams are probably a good start. Also, Old School Coder, who's in the chat, has got some really good content as well. You can join my Discord. We do 6502, so we cover mostly Commodore computers, Commodore 64 primarily, but the 6502 can be used to do Atari 2600, Atari 800 XL, NES, Atari Lynx as well. Apple II, I think, used 6502 as well. And then there's some variants of that as well, like the 6C502 or whatever it is in the PC Engine is a kind of variant of the 6502 with a few extra commands in there. So if you want to do assembly, start here, join my Discord. I'll pop a link to that in the chat. It's probably already been linked just above, but there you go, it's another link. If you want something other than 6502, there's plenty of other places online. Oh yeah, BBC Micro as well, and the Acorn Electron. I do want to do something on the BBC Micro at some point. I started on a BBC Micro, and I've got a BBC Micro back here. Actually, I've got an Electron as well. I still need to fix this. That beauty. Still got an Electron. I don't know what's wrong with this. I do need to take a look at it. I think one of the memory chips has gone in it, judging by what I'm seeing on screen. So I will get round to fixing this at some point. But this is from 1982. But this is 6502 as well. Just trying to think, are there any other 6502 machines? I think that's pretty much it. Is the Electron good for games? Not really, no. I mean, it's got some fairly decent games on it, but it's not really a great gaming machine. It was basically the kind of cut down version of the BBC Micro. It will run things that run on the BBC Micro, but it will run them at a much slower rate. And what was I playing on it? One of the first games I tried on it was Commando, and it was awful, absolutely awful. So yeah, it will run a lot of things, but it doesn't perform as well as the BBC Micro. Yeah, no mode 7 as the coder says. So you got no teletext mode basically. Do I have any complete programs or games? I do have some complete things. So if you go to my, I don't know if itch works on here. Let's try it. No, it doesn't. Okay. Wow, I can't believe I've not got an itch link on there. I should probably get that. Let me find my page. So there you go. That's got my my itch to commit. Yeah, I need to get a commit command as well, don't I? Definitely. So that's got a couple of games that I finished. Well, last year mostly. The most recent one was a charity game I did in a 16-hour stream about a month ago, sorry. And I'm quite proud of it. It's a nice game. If a little bit difficult. People are stressing out over level 24. Well, Hayes is stressing out over level 24. What's in store for Saturday? So I'm going to fix the FLD stuff because I was having a really bad day and I don't think I thought about it that well, and I think I could fix it really quickly. Then we've got the 2-player kind of mode kind of working, so now I'm gonna concentrate on the bonus screen. So we're gonna have a think about how the bonus screen is going to look, how we're going to add score, how we're going to award the crown, and the animations around that, and the kind of view of that, and how the bonus scores work, and then maybe start thinking about the transition back into the game. So we've got the transition out of the game. We need to start thinking about transitioning into the game. I've not got any ideas for that yet, but I'm open to suggestions with that. Maybe have a play around with the transition a little bit as well. I thought some cool ideas for improving that transition a little bit. But yeah, we're gonna work around kind of filling out the game flow a little bit, and then we can kind of work towards graphics. I guess after that we need to start thinking about level design and stuff. Dot Cosmos 2 is, I mean, it's good, but it's just taking some bloody time to complete. I've got a lot of projects on at the moment. Dark Cosmos is, it's not really part, because I am doing kind of graphics here and there for it, and it's definitely a lot further than the video shows on there. Unfortunately, it's broken at the moment, so I can't really show it here. Eventually seems like a lot of time. Yeah, it will get there eventually. I've always said with Dot Cosmos 2 that it's not a game I'm going to rush out. It's ready when it's ready. I'm not gonna stress myself out over trying to meet a deadline or anything like that. And I just want to finish it when it's ready. And it's got to be exactly what I've got in my mind. I've got a vision of what it's going to be, and how it's going to work, and how the levels are going to work. And when it's finished, it's finished. However long that might take. But there's more projects coming this year, so that's pretty cool. Looking forward to getting those out. I'm working quite hard on something at the moment, which I'm hoping we can get out in the next couple of months. Yeah, I can't really say much more than that, unfortunately. Okay, I think I'm going to call it there then, guys. If no one else has got any more questions about maths in particular. Yeah, my problem with Doc is it's the first one was, I always had more idea of what I wanted to do with the first one, and I had to dial everything right back to fit it into 16K. And so with Doc 2 I can do all of that, and now I'm also making sure that I am pushing everything to the absolute limit. So I've got like the 8-way full color scroller, variable speed, things like that, and still keeping the transition, freezing and rewinding time and stuff. So it's going to be pretty awesome, I think, when it's done. I hope it is anyway. I've kind of spent a lot of time on it, and I'm also trying to design it as a kind of speedrun game as well. So every level will have a timer. And a completion level as well, so there'll be a 100% complete runs, and just any complete runs as well, and 1 credit runs, things like that. So there's no, all that happens when you run out, when you lose your lives, is you'll go back to the beginning of that level reset. You won't go back to the beginning of the game. There won't be a limited amount of continues. You can continue from anywhere in the game, so there'll be 1 credit runs as well. And it should all save to the cartridge as well, so whenever you load the game up, you'll have all your times and your completion values for each level as well. So it should be pretty good. PS5. It's probably going to be longer than the PS5 release, if I'm honest with you. Working out the gravitation constant of 2 bodies. Well, I would hope that you could do that with all the stuff that's in here now. You could apply those algorithms to this code and probably come up with that stuff now anyway. Thank you for the follow, Nerigo. Welcome to the stream. Unfortunately, we're just about to end, so yeah, I think I'll call it there. Let's go and have a look, see if we can find someone to raid. I'll put this code onto GitHub when I'm done. Misty K's on. Let's go and raid Misty K. Yeah, I will stick, I don't know, it looks like he's playing Little Computer People. I think that's what he's playing anyway. Okay, yeah, I will put this code onto GitHub when we're done. GitHub link is here. The video will be in the VOD section. I'll edit it down and get it onto YouTube in the next week or two. I'm a little bit behind on videos as usual. And I'll see you guys on Saturday. We'll do some UI stuff. We'll mess around with the game UI, make it look really nice, get that bonus thing working. Okay, see you later, guys. Take care.